Welcome to my lecture. Hope Bea and you had a great time. I was thinking about now combining reactions and diffusion, and first talk about a model which is not really yet a diffusion reaction model, but a model which is basically of the same type. And it deals with dynamics of just classical thermodynamic problems like an easing model. And it asks the question, what is the relaxational dynamics for an easing model in the different phases, low, high temperature phase, and at the critical point. And for that, I would like to remind you things we have already learned earlier, basically in my first lecture about the Landau theory for the easing model. And this Landau theory for the easing model says we have a free energy density as a function of a scalar field. This scalar field is meant to describe the magnetization in a system. And you now say you expand the free energy density in orders in powers of phi, and only even powers are allowed because of the up-down symmetry of easing spins, and that leads you to the Landau free energy density as you have it on the board. It's such that the blue curve that you see describes the free energy density in the high temperature phase, where you have only zero magnetization as the minimum in the free energy. And when you then cool down and change the R value here to a positive value, you are having a double well potential. That means you have a low temperature phase with a finite magnetization, and a magnetization given by the minima here in the free energy landscape. On the right-hand side, you see the phase diagram, the mean field phase diagram, or equivalently the bifurcation diagram, where you start out at high temperature with a fixed point that's zero, that's the paramagnet, and then at the critical point where R switches sign, you have the emergence of a pitchfork bifurcation with phi plus and phi minus being the two possible magnetization states of a easing ferromagnet. So you know that. You also know if you generalize that to include a magnetic field, then you break this up-down symmetry and the bifurcation diagram unfolds into a saddle node bifurcation. And the point is, in the thermodynamic free energy landscape, that now the minima are no longer symmetric. They are biased towards the state where you have the spins aligned with the external magnetic field. And now we would like to study dynamics of those systems and not just the equilibrium steady state. So this brings me to dynamics of non-conserved scalar fields and with non-conserved I mean that there's no constraint on the total magnetization of the system. The total magnetization of the system is free to relax. That would be different for a system that's a liquid. In a liquid, of course, there's a conservation law concerning the number of particles. So what we have is we have a scalar field phi, and the scalar field phi is a function of space and time. And we do have a local free energy density phi of x and t, f of phi and x and t, that describes the local behavior. And as we have it there on the slide, this is something of that type, phi to the fourth. And this is phi squared. Okay? Now, how would you generalize that to space? Right? If you think about space, then in one dimension, if I were to plot the field as a function of x, thermodynamically, you would have something that's just flat and constant, doesn't depend on space. And now you say you have something that varies with space. And you would like to know what's the free energy density that describes such a spatial modulated magnetization. Okay. And then you're led to the following. You say now there is a free energy functional, and this free energy functional is now really a object that depends on the function, the spatial variation, the temporal variation of the density field. And you're saying I have to integrate this over my volume, and let's say we have a general dimension, d-dimensional space, so we integrate over all space, and then we write down the terms that we already have. This is the local part of it. That's the same as before, but now you need to account for the fact that you have gradients in phi, right? So spatial variations. And then the question is, what kind of gradients terms can you write? So let's just write a gradient of phi for a moment. And then you will immediately say you can't write this because here on the left-hand side you have a scalar and now you have a vector. So you need a scalar quantity in there. And this scalar quantity you need in there needs to be one that respects the symmetry of phi to minus phi. So it needs to be somehow square in phi. It also needs to respect symmetries which are rotational invariants in space, because as you turn your sample of your magnet, that shouldn't really change the behavior in any way. Okay, and the lowest order term that you can write down that respects these kind of symmetries, so rotational symmetry in space and up-down symmetry in the spin space, is a gradient phi squared. You can add higher order terms as you can add higher order terms here. Right here you could add phi to the 6, phi to the 8. In the same way you could include here gradient phi to the 4th, to the 6th, etc., etc. So what we say is we do an expansion in powers of phi, and we do an expansion in powers of gradients of phi, thinking of phenomena that are long wavelength phenomena. Right, so we do a gradient expansion, and this gradient expansion means that the phenomena we can describe and want to describe, they're all happening at long wavelengths. And I give the prefactor here a name. Many different things I could call that. Let me check what I did. So I have here plus kappa over 2. Here are higher order terms. And this term kappa here is a rigidity term, which means that as you look here for the free energy, it doesn't want those gradients. Any gradient here gives a higher free energy, or it's penalized. So gradient phi to 0 is the ground state. And the rigidity tells you how much of penalty you pay if you have some gradients, some spatial variation in the density field. Okay? And that's called the Ginzburg-Landau free energy functional. And it's really important that I constructed this just on the basis of symmetry and using this long wavelength argument. Nothing but this. Okay? I do not know when I make such an argument what R is, what U is, or what kappa is. Those are material parameters that depend on the system that you study. And if you were to have a molecular model for the system you look at, you could in principle, from the molecular interaction between the spins, derive the values of R, of U, and kappa as a function of the microscopic parameters. And you're going to do this in the problem sets for one particular example, so you see. Okay, now let's say we have that free energy functional. It's still a functional that gives us information about the equilibrium steady state. What we want is we want to have a dynamic equation. Okay, so what's the dynamics that this system goes through? Again, one could in principle derive that from some more macroscopic model, but here, following the same spirit as before, I'm trying to guess it based on very general principles. So what I will have is that these order parameters, they will relax to the thermodynamic state, right? That's what the system will ultimately reach. And in order to make sure that the system reaches the ultimate free energy minimum, I want a dynamics that goes downhill on the free energy landscape, right? So I want that any kind of gradient in the free energy landscape, and this is now a functional derivative, so I'm varying the functional with respect to local variations of the external field, and I want this dynamic to go downhill, so this needs to be minus those gradients that you have in the landscape, and then there is a parameter that I call lambda, and this lambda is a Onsager coefficient or kinetic parameter. It's again a phenomenological coefficient of which I have no a priori information. It's just saying that this will be material dependent. Good. How do I know that this thing goes down to thermodynamic equilibrium? Well, I can ask, what is the total derivative of the free energy? So as time progresses, is the free energy that I have here really such that it is going to a minimum? Well, we know what f is. F is a function of phi. So I can take the functional derivative of that. That would be df. Sorry, we call this df d phi. So I'm using chain rule here. I'm doing the variation with respect to x and t. And then by the chain rule, I have to add here a partial derivative of d phi of x and t with respect to time. Right? But now you notice this object here, I have written down a phenomenological equation for, is proportional to the f d phi. So as you insert the equation of motion, you find that this is the Onsager coefficient times a volume integral over the variation of this functional with respect to phi and squared. And that has to be positive. Okay? And that means this thing will always be such that the free energy functional decreases over time. In the language of dynamic systems, this is a Lyapunov functional, which is just saying the very same. Lyapunov functional decrease as a function of time. There's one more caveat here is, wait, I'm answering a second. You need to have that this f here is bound from below. Otherwise, you don't converge to the corresponding minimum. You just fall into minus infinity. Right, you had a question?
Yes, there we have an F, a big F or a small F?
It's the big F. So this F here is the same as that, the same as that, as this, as that. Yeah?
I can't understand then the passage from the...
Here to here?
Yeah.
So think of a function, f, that depends on many variables. And think of that in terms of discretizing space into space points, x1, 2, 3, 4, 5, 6, right? Then this is a function of many variables. And as you take the derivative, you get the sum over all partial derivatives, right? And as you make this again into a continuum, you get an integral. So these functional derivatives are just generalizations of a multidimensional differential to the continuum. In case you guys don't know about functional integration or functional derivatives, I'm happy to do some in the tutorial. Okay? So just tell your tutors over Moodle, and then they will inform you about that. It's not a big deal. It's just, as I said, a generalization of multivariate derivatives. Okay? So that's very key. So this set of equation, which is called model A, also the Allen-Cahn model. And what it is called depends on the community you're in. So in the critical phenomena community, this is called the model A by a very famous review article of Halperin and Holmberg that introduced that terminology. And Allen and Cahn were studying this much earlier in a different context, where they just looked at non-conserved dynamics of fields. Okay, so that's our equation. That's model A. And we want to study how it behaves if the free energy functional is given by such a Ginzburg-Landau functional. That's what we want to do. Yeah?
Given that it is a reactional function, assuming model A is restricted to describe a system with a double state of fixed points, since
it's not so much about fixed points here, because this is a spatially extended system, right? So you end up in a thermodynamic state in the end. It's really about the whole function approaching a minimum as you progress in time. So with that, you make sure that the thermodynamic state is reached, right? That's what you want to say with that. And that justifies such an approach as a phenomenological approach because this guarantees that my system relaxes to equilibrium. Okay? Other questions? Good. Now let's analyze that, maybe really write it out. So let me use now this free energy functional and explicitly write the equation of motion. So this then gives, as I do the functional derivative, and by the way, you know these functional derivatives because you had classical mechanics, and there you had the Euler-Lagrange equation. Just have to look back into that. And the Euler-Lagrange equation is derived because you have this principle of least action from which you then determine classical mechanics. Okay? So what I'm doing here, I'm using the Euler-Lagrange equation to take this derivative of the f d phi. And the Euler-Lagrange equation gives you first the derivative with respect to phi. So you just get f prime. And then you have a derivative with respect to the gradients of phi. That's the second part in the Euler-Lagrange equations. And there it comes with a minus. Okay? So what you get, if you do that derivative, you get this is f prime of phi, and from the functional derivative of the second term, you get a gradient squared of phi. That's the equation you do get from this analysis. And I got this slightly wrong. There's a minus here. And for my notational convenience, I'm setting lambda to 1. And that just basically means I'm choosing lambda inverse as my basic time scale. So I'm rescaling time such that the new time is measured in units of lambda. That's my Allen-Cahn equation. And now as you look at this equation, the stiffness term from the Ginzburg-Landau functional that penalizes spatial gradients, it looks like what? Like a diffusion term. Just to replace kappa by d, then this is a diffusion term. Yeah. But this is really analogous to diffusion. And if you look at that, then this is just a function of phi, and you can interpret this as a free energy landscape as we've done so, or you can interpret this as a reaction term. So you can write this also as r of phi, and then the whole equation is a diffusion reaction equation. That's not how we derived it, but the mathematical form is really identical. You have a diffusion term, and you have some kind of nonlinear function that is a function of phi. Okay, so that means this is equivalent to a diffusion reaction model, and we will later see what kind of chemical reactions you can come up with that give a reaction term that has the same structure as the derivative of a Landau theory, which is this double well potential. Good. Now, how do we analyze such a Allen-Cahn equation or diffusion reaction equation? The first thing you can do and should do is linear stability analysis, also short LSA. And this linear stability analysis says, let's assume I have a thermodynamic state, and let's call this thermodynamic state phi star, which is spatially uniform and time independent. So when you look here at this graph, you could say, let me assume I'm here at this phi star, or here, or there. Okay? And let's now analyze of what happens with the linear stability of this phi star. You know the answer actually already whether that's stable or not. So what about this point? It's better stable because thermodynamically this is a convex shape. This is also a convex shape. So these phi plus and phi minus, they are stable. This one is a point which is concave. And the free energy that's concave gives rise to instability. So the middle point needs to be unstable. And if you start with a system that you cool down to a very low temperature and is spatially homogeneous, you're here, then you should slowly converge to a system where you have a finite magnetization. That's what you expect on thermodynamic grounds, but we can also derive that from the dynamic equations that we have. So what we say, as I just explained, we say that the spatial profile of my magnetization is a constant plus small deviations delta phi with respect to the small constant phi star. And now I insert this linearization ansatz in my equation, the Allen-Cahn equation, linearize in delta phi, and just neglect all the terms that are higher order than linear terms. So I replace it by a linear equation, And then I want to learn from that how initially for small values of delta phi, how do they grow or shrink with respect to the homogeneous state. Okay, so if you do that and linearize, you get dt phi of x and t is given by, well, let's linearize the reaction term or the free energy term first. So this will be expanding around phi star. F prime of phi star, these are minima or maxima, is 0. So there's no contribution. That means the next term that we have is the second derivative evaluated at phi star times delta phi of x and t. And then the term coming from the stiffness is just kappa nabla squared delta phi, because nabla squared acting on a constant is 0. Right, so we have kappa nabla squared delta phi of x and t. Now when you look at that, this is basically a diffusion model with an extra term. And you've learned last time in the lecture that Bayer gave that if you have a linear problem like so, the way to solve that is by going to Fourier space. Because once you go to Fourier space, this nabla squared turns into a wave vector squared. That's what we do here. We make a Fourier ansatz. So we say that I'm decomposing phi of x and t into Fourier modes Q in the following convention. This is my phase space factor. I have here a plane wave factor Qx, phi of Q and T. And when you do that, then your differential equation turns into a very simple algebraic equation for the Fourier modes. So phi of Q and T has a time evolution which is given by minus f double prime at the homogeneous steady state phi star times delta phi of Q and T. Then here you have a minus because of the Fourier transform with the I, minus kappa Q squared delta phi of Q and T, right? This is my Fourier equation. So on the right-hand side, you already see that these are the eigenvalues of your problem, because I've diagonalized the problem by using Fourier modes. And that means what you have here as prefactor in front of the delta phi is the growth rate of the mode phi of Q and T. So the mode, if I make this ansatz, delta phi of Q and T being proportional to the e to the plus sigma of t, right, then I can insert that here. I have sigma, sorry, I should write here delta phi. I have sigma, delta phi is the right-hand side, so the growth rate sigma is the right-hand side. And it depends on the wave number q. Sigma of q is minus f double prime at phi star minus kappa q squared. That's called the dispersion relation. And this dispersion relation gives you the growth rate of your Fourier mode Q. Now let me plot that so you see what this means. Let us plot here sigma of q as a function of q. And remember, there are 3 points I want to expand around: the minima of the free energy landscape and the maximum of the free energy landscape. At the minimum, you have f double prime being what? Positive, right? It's opening up to the top. So for that case, I have here a value at q equal to 0, which is negative because f double prime is positive. It's at the minima phi plus minus given by the square root of r over u, we have f double prime of phi plus minus is positive. And that's very important because the second term is always negative. It's minus a constant that's positive times kappa squared. So your dispersion relation is starting from a negative value and it's bending down. All the growth rates are negative, meaning all the Fourier modes, if you start exciting them, they will decay. Okay? Nothing will happen here. Homogeneous steady state is stable. Okay? Homogeneous steady state are stable against spatial perturbations. What about my maximum phi naught equal to 0? Okay. So remember, this goes down and up and down. So here you have f double prime being negative. Right, there you have a concave shape. So this is negative. And that means now I start at q equals 0 with a value that's already positive. And then again, I'm bending down because minus kappa q squared is always negative. So for phi 0 equal to 0, and this is for phi plus minus. And now you have a band of unstable modes, right? This here, this whole band has growth rates that are unstable, and therefore if you start with Fourier modes in this band, they will exponentially grow, like so. Because of e to the sigma t, all these modes will be hugely amplified along the way. When is it 0? So here, when does this curve that has the dispersion relation, when does it pass through 0? So when does it first become unstable? Well, it passes through 0 if your double well potential becomes the first time a double well potential. Because there you have this sign change in f double prime. So this here, this particular case, the critical case, is where you have the critical point. Right here. This is at t equal tc. So the phase transition here shows up as an instability of the 0 magnetization configuration to small spatial perturbation. And now imagine you are here in the high temperature phase and you drop your sample into something super cold. So you quench it very fast to a low temperature state. And that means you start out with an initial condition that's homogeneous and flat. And then the system will evolve. So we quench it down now from here to there. And we want to know what the outcome of such a quench is. And for that, I'm going to show you a movie. So this simulation here does the following. It takes this Allen-Cahn equation, puts it on a software, finite element solver, and solves it. The software is very publicly available. I can point you to that, so you can use these kind of softwares. You can also write the program yourself. There are simple Python codes that do that. So here, what you see is the initial condition. And the initial condition is green, meaning phi is 0, as you can see from the color bar on the right. So I have chosen a system to be quenched from a high temperature phase to a low temperature phase such that the initial condition is a steady state with phi equal to 0, no magnetization. And some small perturbations that you can't see. So some small delta phi's that I randomly add to the data. So now as I start the movie, what you should see is that there is this band of unstable modes that grow, right? Because they are amplified. And the small wavelength modes, they are attenuated. And that means when I start from a wide spectrum where I have all Fourier modes in there, you should initially see that this wide spectrum becomes coarser because the short wavelength fluctuations will go away and the long wavelength fluctuation, they will be amplified. And as you see here, right, those which are having the longest wavelength, they will be amplified the most. Good. So let us look there. This went very fast, so let me go back. So and run it slow. So here is the initial phase. And this initial phase is a randomness, but very quickly, as you can see here, there are wavelengths which are longer that dominate. And as time progresses, the wavelengths that dominate become even longer, and you start to see interfaces. And these interfaces that you see here, they are no longer part of the linear stability analysis theory, but because I didn't talk about strong perturbations, I talked about small perturbations. So the analysis that we made is for this initial phase of amplifying long wavelength modes. And then I let it go, and the system evolves into very clear-cut interfaces between high and low density domains, or between domains which have spin -1 and spin +1. -1 is blue and +1 is red. And you see the emergence of an interface. And you also saw, maybe let's go back. Now it's getting boring. So if you go back, like here, so what kind of tendency do you see for the interfaces? Do they become longer or shorter? Shorter, right? They become shorter, and if you look at the curvature, so interface length is minimized here as the dynamics progresses. And if you look at the different curvatures, there's things that are outward bent, like the top one, and inward bend, like the one at between 100 and 125. And the inward bend moves out, and the outward bend moves in, ultimately straightening out the interface. Okay? So what you see there is that later on in the time evolution of the system, you have a new excitation, a new meta state. This meta state is an interface, and it has a dynamics that looks like the interface length is becoming shorter. And that effect is called a surface tension. And as you know, right, if you make bubbles out of soap, then you know that these bubbles tend to have minimal interfaces. And here, at the very late stages, you have almost no curvature anymore. And when you have almost no curvature anymore, the dynamics goes very, very slow. Only if there's curvature, as you saw, the dynamics is driven towards the straight state. Okay, and what I'm going to show you later after the break is how you then make a theory for these interfaces. And then combining the linear stability analysis for the early time evolution and the interface theory, you understand then what goes on in the full nonlinear dynamics. So let me show you the blow-up, starting with some random initial state. Here all kind of a wide spectrum. In the wide spectrum, the long wavelength modes get amplified, and then you have the interfaces. They evolve according to surface tension. This here now is a different initial state. Same kind of dynamics. All I changed is the initial state. And in that initial state, you get just a single domain with -1 spins. So in the magnetic analog, sequential magnetic system, here it will find a magnetization that's homogeneous throughout the system. And of course, the same can happen with +1. If I choose different initial states, I could also have just a red surface. And this state here, note there's this periodic boundary condition that's called a kink and anti-kink state. That's not really a stable state. It's a metastable state. If you were to wait long enough, and that would mean very, very long, the system would finally flip to a state where you have all blue or all red. Because those are the two minima in the free energy functional, and there you need to go in the long run. It could just take a very long time until you reach that. Right here again, initial spectrum, long wavelength modes are amplified, small wavelength modes are attenuated, you get interfaces, they coarsen, the system goes to the thermodynamic ground state. All right, do we have questions? Yeah.
In the beginning, we see the effect of adding an external field H5 on F5, but here, given the second derivative in sigma q, then does mean we wouldn't see it.
So we have no external field here. That's quite important, because if you have an external field, you break the symmetry between spin up and spin down, and then these domain walls or interfaces, they would move. Right here, they are straight, and +1 and -1 are equally deep minima, so they are equally likely in the free energy functional, and therefore this interface stays steady. I'm going to show you how this works in terms of math. If you make one state more favorable than the other, then you start developing an interface with a velocity, and this velocity would then move out the domain that has the higher free energy and give rise to a ground state with a lower free energy. So when you go back to this figure of the free energy, here this has the higher free energy, that has the lower free energy. This one would be the ultimate steady state. Yeah? Other questions? Good, then we have a break for 15 minutes, and after the break I'll show you the interface theory.